Okay, in this video I want to cover something that's been just very fun for me to experiment with recently as part of my exploration of Forth. The Forth language, if I just look for the Wikipedia page, Forth gets described often as a stack-based programming language. But it has some interesting features. When I had learned in college, in a survey course over several different programming languages, I learned Forth as a stack-based programming language. But I didn't understand or wasn't exposed to some of the depth that makes Forth a very, very interesting language. These days, Forth is not extremely popular, but it does still survive, some people would say, as a niche or niche language, maybe applicable primarily to embedded programming. This video is going to be about some practical embedded programming using it. Bear in mind, I'm not really a Forth expert by any stretch, but certainly enjoy a number of different programming languages. The specific Forth I'm looking at is the Mecrisp Forth compiler, which was originally for MSP430 microcontrollers, but then recently has been ported to the ARM Cortex series of microcontrollers. And it's really an amazing work of art, in my opinion, the more I've dug into it, and actually have learned quite a bit about implementing similar types of interpreters or compilers just by looking at the source for this one. But what's really neat about Mecrisp is that it supports a large number of target devices. I have done some experimentation with some of the Nucleo boards, some of the discovery boards for STM32s. Also had picked up a Tiva launchpad, actually as the connected version with Ethernet. And that's cool, but it's a $19 board. And I've always been interested to try to find something that would be fun to play with these little cheap boards here. On the Mecrisp site, it's called the Shenzhen LC Technology Board, but usually on the internet you'll see it called the Blue Pill. You can see that with inexpensive Asian suppliers you can get these things for $1.80. There's an issue with this particular board, which I have a number of. It has a broken resistor that means USB doesn't quite work, and I have to do some surgery at some point and fix that. I also have some of these coming in, the so-called black pill, which may fix that and may actually work out of box with USB, but I don't have one of those yet. So I have my little rig for now, but to me the idea that I can use an extremely expressive and high-level language to do interactive programming on a $2 microcontroller dev board is just unbelievable. So let's hop into it a little bit. Here hopefully you can see I've got one of these little Blue Pill boards. I'll go ahead and plug it in with power, but recognize since USB doesn't quite work because it does have the broken resistor, till I fix that, I'm currently running a Teensy as kind of a UART proxy. So this is really, it's just running a small program that says anytime a byte comes in or out from either side, send it to the other. It's just a little serial relay. So really I'm just talking to this over normal serial lines. So let's plug this guy into power. Now I've already burned the Mecrisp binary image to this particular board. It isn't too hard. I did it with just a regular ST-Link. You can find a lot of stuff on the internet for how to burn something to an STM32. What's more interesting is how you connect to this thing. So Forth is, by its nature, an interactive programming language. And it's not that there aren't Forths that support a write code and then compile and execute sort of work style, but traditionally speaking, it's an interactive thing. So there's a terminal program. There's a little bit of a quirk with the way Mecrisp does its terminal interaction. So the project includes a small script that handles all the right settings for you to connect to it. And once connected, you can see it's 115 kilobaud on, there we go, whichever USB device shows up in /dev. And when I start to interact with the interpreter or the compiler, I get a prompt. Anytime I submit something, I get an OK once that something has been interpreted. As I press enter, I'm just submitting something empty, so empty does nothing and then has been interpreted. But we can use this as often build basically a stack-based programming environment. So I can put numbers on the stack. If I examine the stack, we can see that we've got, you know, my 1 and my 3. I can add these two, and then I can print out the results. So 1 plus 3 is 4. Fortunately, that went well. You can even do things like we can define a function, so we can say, actually, if I do this the more traditional Forth way, we do the carriage return first. And then if we run that word, we print hello world. So this is kind of normal Forth. I'm not going to go deeply into the syntax for the language, but suffice it to say, hopefully you can see that this shows that I'm interacting natively with it. I'll actually show some interesting details about how this gets implemented underneath and some of the fun of working with this in an interactive environment. So one of the interesting things, and I think if someone's coming from more of an Arduino or Mbed, or maybe even from the manufacturer's CMSys C library sort of approach to embedded programming, what I'm about to go into is probably going to seem a little bit unfairly low level, but the fact is, a lot of times when you're using Arduino or something along those lines, you don't realize how much it's doing for you already. So every microcontroller, especially in the current ranges of ARM microcontrollers, they're very complicated. There are a lot of different ways to connect paths through the microcontroller, and so there are a lot of control registers and other things that need to be handled in order to configure the peripherals. And a lot of that gets hidden through some of these other environments. So I'm just going to do a little slightly more complicated than Hello World program, and hopefully get a chance to give you an idea for what this looks like and demonstrate some of the features. So some of the things we would need to know, if I want to do GPIO, I just want to be able to send signals out on these pins, then I need to be able to turn those things on. There are a few constants I'm just going to throw in here real quick that I looked up in the datasheet. Unfortunately for the STM series, I personally don't like the way the datasheet lists these. It requires me to look at several different pages to piece together where these addresses are. It can be quite frustrating. Actually, we want another C in there. So this register allows you to enable or disable the GPIO ports. And then this one is the low half control register for GPIO A. So there we go. And this would be the output data register for port A. This is the kind of thing where normally I think if you're using the typical maker-friendly dev environments, you don't really have to think about this kind of stuff. These things are already wrapped up in constants. And bear in mind, you shouldn't hold that against Forth, or Mecrisp, because this is something that has to be done at the library level. So Mecrisp is not, doesn't handhold quite so much. There isn't so much library already. There is actually some of this defined in some Forth programs or library files that come along with it. I'm just going to do this bare here just to illustrate how this works. If you're interested, you can even explore these kinds of things. Like if we take this constant and we define that, we can now print out its value. Currently it's 0. That would suggest that not very many of the GPIO ports are actually enabled. This is just Forth syntax. You put an address, in this case it's a constant, so this number gets put on the stack. At will fetch that address and put its value on the stack, so it's basically dereferencing the pointer. Hex switches the output mode to hexadecimal because it's much more fun to print 32-bit words from memory as hex. Dot prints out the thing that's at the top of the stack, and then decimal returns us back to decimal. So that one's maybe not quite so interesting. There's some other registers that would certainly have data. But we can start to explore these, and I've found as I'm working with the chip and I'm trying to figure out how from the sort of bare board level I need to interact with it to turn on features and use them, this ability to interactively check and see what the value of a register is really great. I don't have to recompile my program and then send it out to the device and then have it print out something on standard out. And I also don't have to connect with the debugger through the software debug interface and then use that to try to figure out where I can put my jump point and where I can print out some location in memory. This actually turns out to be a little bit more convenient. It's much more like programming in Ruby or Python or Lisp or one of the other languages that I like to use in a full-size operating system environment. You get an actual REPL. So we'll take these and let's initialize our GPIO. Like I said, this is the kind of stuff that often gets handled in a library for you. So on the STM32, this is the right way to turn on GPIO A. There's a different bit for each of the ports along the way in this register. So here we're just saying, actually I want to do it this way. Even though it is starting out at 0, who knows where it is somewhere else in my program. So I'm going to say, take this bit mask, and BIS bang is just a convenient way that Mecrisp gives you to do an in-place update of the register. So whatever its other bits are, it's going to set all the bits that are a 1 in the mask that you send it. So I'm basically saying, set this bit to 1 and leave the rest of them the way they are. And then for a lot of microcontrollers, you have to decide what mode the GPIO pins should be in. They have lots and lots of modes, and so we'll just set this up. This turns out to set them up, I believe it is to set them up as outputs, and they're going to be push-pulls, and I think it's the 10 megahertz speed because you can determine what the rise time is for signals going out on the GPIO pins. This is just a fairly standard way to configure them. And if we want, we can just take this, I'll reset the microcontroller, and we'll load this up. So all I'm doing here is in the terminal inserting this file, but now we have these functions, so I can call GPIO init, and thankfully it's okay. We didn't throw some sort of exception that wasn't handled, which is how you find out there's an error usually. But now I can take one of these registers, and we'll see that, well, somehow that one's still a 0. It should have a bit. Let's see, this one successfully went. This one might not actually show the value after you've set it, I'm not sure. We'll just roll with that. So something we'll have to do to make a properly interactive and visible program is we need to be able to do a delay loop. There certainly is a timer that I can set and actually measure time in milliseconds, but just to do this the easy way, we'll just do a loop that does nothing. So here we're just, for 200,000 iterations, we're going to put the counter on the stack and then drop it from the stack. So this is just busy waiting. Should take a little while to run. We can see how long that's going to be by compiling this, and if we wait, you can see there's a short delay there. Let's do it 10 times. We'll see how long 10 waits is. Oops, there we go. So that's a reasonable amount of time. That'll let us see, if I start changing these GPIO pins and the LEDs flicker, well, if I don't do it slowly enough, we won't be able to see the result. So this gives us a little delay loop. And as you can see, we can run it just by using the name of that word. We'll also want to have something that we display out. I've already kind of decided what I want, and we're going to create a variable. We'll call it the val, and occasionally we'll need to increment the val. So what I want to do is I'm going to take the variable, grab its value. I'm going to add 1 to it. I'm going to AND it against 255, so that's just going to mask it off to 1 byte. I probably don't actually have to do that, but it's cleanly, so I'll do it that way. And we write it back out to the location. If you're not familiar with Forth, what this is would be roughly the equivalent in C of saying val equals val plus 1 and OXFF, something like that. Now, one of the things that I often encounter as a criticism of Forth is that this seems nigh unreadable. Some people call it a write-only language. But you have to realize that this is only readable because it's capitalizing on some syntax we're used to from math when we were kids. And actually, as I was pointing out to someone recently, it isn't even correct, because in math you can't say something like that. You can't say that val is equal to val plus 1, because now you have two conflicting definitions, actually an infinitely recursive definition of val. And that's not really math. It's not really a valid mathematical expression. But it has the appearance of mathematical equations, And we kind of recognize that. And so sometimes it's easy maybe to say this makes more sense. But trust me when I say once you get used to reading this, it isn't so bad. This is a very common pattern for I'm going to grab the value of a variable, I'm going to do some postfix math with it, and then I'm going to set the variable again. So this way our program is occasionally going to increase the value. And then we want to display the value. Displaying the value really just means we grab the value from memory, and we're going to write it out to the location of the output data register for GPIOA. CBang, all that does is store a single byte. It's going to assume that this is the pointer to a single byte and write that out. Actually, doesn't matter in this case because I'm not using the rest of the GPIO port, but it's cleanly. So we'll do a single byte. It's a character in Forth. So we can, at this point, we should actually be able to experiment with this. I'll reset and reload our file. So if we GPIO init, that gets us some ports. Now if we just display now, of course, oh, whoops. Make sure we get the actual, there we go. Forgot to save it. We need to have these definitions. We'll initialize GPIO. If I display, nothing interesting happens. But what if I set a value to that value? We'll just say, what's an interesting hex value? Maybe it's C5 is a good value. There we go. Now we can see C5. We had first 2 bits of the first nibble and alternating bits in the second nibble. There we go. We're successfully seeing it. If we set this to 5C, which will change, or we can display it differently. And even right here, hopefully you can see this is kind of interesting, or at least it's interesting from my perspective, having played with PIC microcontrollers and AVRs, and as well as some STM32 stuff more recently with other language environments. If I'm writing this in C, this kind of live real-time exploration to see if my code is working so far is a lot harder. I have to go through full compile and program cycles, killing that firmware slowly over time. Just to see if these little things are working. If I had a problem in here, I'd be able to detect it fairly quickly, whereas in the other paradigms, I'm either going to be working through a debugger or something else, which gets kind of annoying. So some of the value of the Forth style of programming, or the paradigm, is, I think, already showing through here. So once we have the ability to display a value, we know how we're going to increment it, we can get to the guts of the program, which is we're just going to make a little binary counter. So for binary counter, we want to begin a loop. We're going to increment, we're going to display, and we're going to wait. And then here's a little something that you don't usually do in an embedded context. I'm going to check to see if a key has been pressed. So recognize this is operating through a serial terminal. I can type a key at any time. If a key gets pressed, then I'm going to exit the current definition. This is just a convenient way for me to not have an infinite loop that I can't get out of and then continue to interact with the environment. So we finish up the loop, so everything between begin and again is just an infinite loop. Somewhat infinite, if we have some way to get out of it. And then we'll wrap this up with a little main word, which is just going to initialize the GPIO and then run the counter loop. Save that. So now we should be able to run this thing. I don't see any errors. Everything said OK afterwards. Actually, there's a little quirk there. If I don't have a new line or something after here, then I'm still in the middle of typing that word there. So we'll make sure we get that OK coming after main. If we run main, we should see a binary counter. So this, I think, is a little more interesting than the blinking LED. It does a few more things, at least. You can see a couple features. You can see how we use variables, we define constants, we're interacting with memory. But also, I hope you can see that with the counter word here, we're reaching a fairly high level of expressiveness. To me, this is very beautiful. And in a much more complex program, the distance between the top layer of the program and the component parts that make it up is much farther. And what I like about this is, instead of C, which somehow, it's not that you can't write nice high-level expressive C, but it's that people usually don't. Whereas in this case, kind of like Lisp, where you build a domain-specific language up to express your problem. You do the same thing in Forth. You build little primitives that can be composed in a very natural way to make high-level program logic very easy to read and easy to understand. If you want to get into the weeds and figure out how these things work, you can, but you can see what's going on at a pretty high level, basically by reading it in English. So this is fun. This is fun enough as it is. If all Forth was the ability to write programs and things, then that would be one thing. But Mecrisp is this really interesting beast. It's an optimizing native code compiler. And if you wonder what is going on in the microcontroller as I'm submitting these words and they're getting interpreted and actually compiled, and where are all these things going? And so one of the neat things about Forth is it's extremely transparent. If I pull this window out a little bit bigger, there's a word called words, where you can see all of the words that exist in the current image. So starting all the way back with some placeholders here for the IRQ callbacks, we have lots of different words which you can think of as functions defined in the image. So we have things like, remember seeing loop in there, we did some loops. We did begin and again. These are for doing infinite loops, and these are written in Forth most likely. Some of these will be written in bare assembly, some will be written in Forth. But if we go up, we can see eventually we'll get to the layer where we've got our program. So the core Mecrisp API, if you will, is from this point down. And if you look at the addresses, in case you're paying attention, this is in firmware. So these ones are all merged to firmware. Every time I type reset and reset the interpreter, all of these definitions go away, and we return to the status of Mecrisp at this time. At any given time, I can change compilation to start writing new definitions to the firmware, and I can expand that so that they survive, which means I can play around here and probably mess up just about anything in the microcontroller and still recover by doing a hardware reset. But as I reach the level of maturity that I want in my code, that I want it to start becoming persistent, I can cause it to be compiled to firmware and survive past a power off or a reboot. What's neat about that is it means that once I already have the Mecrisp base image burned to the microcontroller, I'll never actually use ST-Link again, unless I really mess it up and have to restart from scratch. But it means that I'm not doing firmware writes all the time. It's very different from other microcontroller contexts. But there's also something else I wanted to show in here, and that is that you can get into examine what these things are doing. And in fact, something I won't get into, and I've actually done a couple times, is you can write words that get executed during compilation. So if you want to do something to the resulting compiled code that is not supported by the language, you can add that really easily. And maybe the best way I can just at least give a basic sense of that is by showing the contents of memory here. So I have written another little library for hex dumping. A lot of Forths include a hex dump utility built in. Mecrisp, I don't believe it does, or at least I haven't found one anywhere in here. So we can do interesting things. Like if we look back at our program, we see that our first definition is GPIO init. And actually, if I scroll up here, the first definition in my hex dumping utility is ESC for typing an escape character. So if I use the apostrophe word, I can get the address of the executable code corresponding to that word. So I can find out where ESC is. It's at this location in memory. If we do this in hex, we'll see it's in memory. It's one of these in-memory compiled functions. If this was a 0, it would tell us that it's in firmware somewhere. But anyway, this is where we see the location of the ESC word. We can find out where GPIO init is here. And if we wanted to, we can see that the code in this Emacs buffer over here, oops, subtract it, there we go, takes up 310 bytes of memory. It actually turns out that when you define your constants like this, the name of the constant gets put in memory. So one way to trim these down is to not use actual named constants, but 310 bytes isn't so much when you're talking about 32 or 64 kilobytes of memory on the box. And if I take this, I can take the GPIO init functions location in memory, and let's back up a few bytes and hex dump it. So we can see the actual contents of memory. Normally you would do this through a debugger probably, but I can do it interactively through the Forth interpreter as well. But perhaps more interesting, I just want to give a sense for where we're going with this. We found out that this little program takes 310 bytes or so of memory, so let's do 326 bytes from 16 bytes before it started. That just lets me show a little header information. I'm going to use another feature of my hex dumping code, and we'll pull this out. So this is the exact contents of memory starting at the definition of GPIO init. If I take that, you can see I've done this a few times, I can paste that through a utility that will decode the hex into raw binary and write this out to a file. And then we can open this in a tool that lets us examine the binary. So this is the same thing. If we could probably compare it if we really cared, but I'm fairly confident it works. You can already probably see something in memory here that we've got the names of each of these definitions. And of course, for the Forth compiler running in the interactive context here, it needs to know the names because it has to look these up by name when the programmer references them that way. And there's a little header information. If we go to the beginning of this one, you can see there's a 9 here. Well, how many letters do you think are in GPIO init? 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't count the A there. It's printable, but from here to here is 9 bytes. So we got a little header, we got 9 bytes, and then right after that, actually, at this 41 byte, this is the beginning of code. And just to give you a sense for what's going on here, we can tell our decompiler here that this is a function. We can see the actual compiled code in here and what it does. Now this one isn't particularly interesting because you can see it's just taking a couple locations in memory and writing out the numbers that we tell it to. But it gets more interesting if we hop back and look at a more complex function. So counter was the main function in our program, and it's got a loop and it actually does some things. I want to show what to me was just really surprising and quite amazing with Mecrisp. So this is the decompiled code in that definition for the counter loop. And one thing I want to point out is there's only one call to an external function here. If you look at the source code, we've got a number of functions. We're calling increment, we're calling display, wait, we're checking whether or not there's a key. We would normally expect, if these are compiled in kind of a naive way, that each of these would be function calls. But Mecrisp is an optimizing native code compiler. So in some cases, you'll see that it's just inlining the functions. So if we were to look, we could find the definition of, let's do definition of increment. So we'll go back to our hex editor. Where's increment? There it is. So let's make a function here. Yes, it's thumb embedded. And so here we're going to see there's a particular place in memory that we're grabbing stuff. I'm not going to look at it in too much exquisite detail, but this looks the same. There's that same address. Yeah, this is just inlining that function. But you'll see also sometimes there's some register optimization because Forth can be a little inefficient if you really treat it with a stack. You'll actually see some register allocation to avoid stack manipulation in some of the functions that get compiled by Mecrisp. And then, of course, there is the one function call. For whatever reason, the compiler decided it can't inline this one. And so this one is actually the wait function. So this one, if you remember, is starting with some nice big value and then counting down until it exits. So this is what really impressed me about Mecrisp is it's a native code optimizing compiler that runs on the microcontroller. Whereas normally you'd think of running your GCC compiler, which is a massive piece of software that compiles your code into the firmware binary that you're going to write to the microcontroller. And that runs off system because there's no way you could run GCC on this little guy. But it can run an optimizing native code compiler in Forth, and frankly, this program isn't all that much more complex than the equivalent program in C if you consider that this is doing all of the underlying library stuff, defining the constants and setting up the GPIO and things like that. My 11-year-old son came in earlier today, and I said, "What do you think of my program?" And he said, "Wow, that's really short." Not that he's an expert on program lengths, but he's seen a lot of programs that I've written, and he knows that this is kind of short. So hopefully this has been an interesting video playing with Mecrisp. I don't have to do things this way. This is very naive. You can certainly configure the sysTick timer, and you can do millisecond waits, and you can set up interrupts and other things. I've successfully used the I2C components in not this chip, but in the TI chip on the Launchpad. I'm hoping to expand and do all of those things on this chip as well, because I have some projects in mind. But hopefully this has been a good little tour, maybe different from your typical, hey, look what I did on a microcontroller video. But hopefully I'll have some more of these in the future as I expand my knowledge of the STM32s from the bare chip perspective, and also getting more done in Forth. So thank you very much.